let me say the title says that is a transition formula. But what's a transition formula? It's hard to say here. But what I can tell is this talk will be very elementary, very, very simple. And we just, at most, we use a Poisson summation formula. I just use a result. So we start, maybe in some standard notation, we say the T is a large pyramid. In our question, we assume T approaching infinity. We introduce another parameter, it is n. N is a fixed power of T. I say the C is a constant. Of course, it's positive. And also, we say the epsilon is just arbitrary small constant. And we introduce a function. I say this is a very standard in analytic number theory, but I would like to mention the e of x. It is the exponential e raised to 2 pi I x. And also, we just write down delta is just slightly smaller than t by a logarithm factor. Our question, we consider a weighted with integral, or we say it is a mean value of Dirichlet polynomial that is in this way. I is equal to, we take the integral from minus infinity to infinity. And we say this is a Dirichlet polynomial. It's like this. The coefficients are a n. These are constants. N raised to minus it. We have a square. Then we put a weight. This is the Gaussian weight should be like this. It's here we have delta. So if then this weight, the exponential just makes it the integral mainly is concentrated if t is close to the capital T. So at least, I say this is formula 1. At least we know it's very elementary. It's greater than by a constant factor. Should be like this, yeah. This without a weight. We just consider this one. Now the results about this one in number theory. Let me first state the known results. But these are only, in general, for the general coefficients a sub n, this is the only known result.
That's bigger than that, but we should have in mind that your width of integration is length delta. I mean, it's bigger, but essentially it's length delta.
Essentially, the length is there.
You're looking at the mean square of the Dirichlet polynomial over a short interval of length delta with delta t over log t, about centered at t.
Yeah. Anyway, because this delta is not too small, it should be close to t. So we may say this is from the t over 2 to maybe 2t something, but not at 0. Not at 0. We avoid the equal to 0, the small t equal to 0. The known result is, let me write down here, I is equal to, we say the main. Because we have the delta, we have this factor, so the integral gives us the square root of pi coefficient plus n arrow, depending on n. Here it is just, we say that, over the absolute square of the coefficients. We only know this. So we know that in case, because n is the power of t depending on the exponent c, So if C is less than 1, almost it's down. This is the major part, delta. Delta is close to T, but this is smaller. But if C is greater than 1, maybe C equal to 2, but it is a fixed constant, what we can know is in general a upper bound I say this is the label 2. I just put here. Label 1 is over there. So we say the formula 2. We may ask, of course, if n is equal to, say, the t squared, t cubed, maybe t raised to some 100, this upper bound is very, it should be, maybe it's very large. But what we can say, this formula is cannot be, not can be, cannot be, sorry, cannot be substantially we say sharpened. In general, we cannot say we get something more, something better than this, sharper than this, because, for example, if you choose n equal to it, then this upper bound is precise. We cannot do. Then we may ask, we say we cannot do, in general, give a just a sharper bound than this. Then how can we do? But before that, let me mention something in number theory. For some, if the coefficients a sub n has some arithmetic meaning, I say arithmetic, one claims that, we say claims, but we are unable to prove it. Yeah. I is less than, the n should be replaced by t. Maybe at most we have epsilon power, that doesn't matter. I say this is formula 2 prime. And here, maybe it's for any fixed c greater than 1. And this formula, if it is for some coefficients a sub n, for every fixed t greater than 1, this is true. Then we can do a lot of things. So we say an is equal to numbered n. This is the, just like the prime character function. O mu n. Maybe my statement may not be, we may need some modification, but essentially it is. This is equivalent to the Riemann hypothesis. And if for an is a divisor function, the case, we say the divisor function. And for every k, for every c, then this is equivalent, essentially equivalent to the Lindelof, right? Lindelof, it is weaker than the Riemann hypothesis. But anyway, this is an important hypothesis. And a lot of things. But in general, also we know that we are unable to make it sharp in general. Then I try to introduce a method. It is actually, let me say again, it's very, very elementary. Maybe it's too elementary to be presented here. But it could be, sometimes it is a little interesting.
One thing you should also keep in mind with elementary is difficult, doesn't mean easy. That's not the problem.
And we say I just say the transition of I.
Selberg, when he was asked what's the field of mathematics, in late in his life would say elementary mathematics.
And also, I'm not going to just, not like as usual, we give the statement of the transition formula, then we give a proof. Because the proof is short, I try to step by step to introduce, then eventually we can see what happened. So first we assume C is greater than 1, and the coefficients I'm not going to repeat this interval or something like this. We just say this set is support on the interval. So n, maybe m, they're always between these.
Let's understand a few ground rules here. The first inequality you gave is a bilinear inequality for arbitrary an that cannot be improved.
Yes.
But you're not going to make an special. You're going to reformulate the inequalities in terms of other conditions in an. Is that the plan?
Mm-hmm.
You're not going to input divisor or anything.
No, but also let me just impose just one constraint.
Okay, yeah.
So we just like this. Then we first we recall that the 2 is equivalent. We may rewrite it. It is, say, the I is less than n, but this sum we may write down it in this way. Here we have the function e. That's the same, right? Now let's see, can we do something, change this one? But it's similar to that. Now we introduce a linear just exponential, just like with the coefficient a sub n e raised to minus n alpha, linear. Let's see, how can we do? So first, we know that because this is the square meaning, we take the absolute value then of the sum, then square. The first way, it is very simple. We square out. Then we take the integral term by term. And so we have the I is equal to, let me rewrite the double sum. The second one, because the a sub n could be complex or something. We take the integral, each integral. Thus, it is direct. To get that, let me give the result. We just make a substitution, v equal to t minus capital T. It is equal to square root of pi, then delta, then double sum. I say this is formula 3. Then in this expression, in particular this exponential factor here, we try to make some modification. We take another parameter, r equal to n over delta. We may need a little slightly larger. So for n is in this interval, and if the distance between m and n is greater than or equal to r, that implies we can verify this part in the exponent is greater than or equal to. In this case, this implies the exponential factor in formula 3 is small. So we just forget about these things. We skipped these terms. The contributions are very small. M less than n is greater than capital R. So we make substitution M equal to NR, and we assume, we just consider that in this case, we get a formula approximately I is equal to, approximately equal, but the arrow is very small. It is n an m is equal to n plus r. Sorry, the log square. Then we make an approximation as usual, because R over N is not large, it's small. We have a restriction here. So in this case, the logarithm of this one is approximately replaced by R over N. Then this factor, because this is, we may rewrite it as the exponential of the logarithm of 1 plus that, something. So is approximately equal to e raised to minus r minus I capital T R over N. This could be rewritten as, using our definition, E of X. And also here we will have some arrows, but we may use a Taylor expansion of these things to do something more precise. But here we just use these. Then the result, let me just state here. Also work? Okay. Okay, just let me write down here. I is equals, also we have a factor like these. Here it is n, it is r, a n bar, a sub n plus r minus tr. Here is 2 pi n, and here it is the x. But here we have an arrow. This arrow is not too small, but in comparison with the formula 2, it is small. We have a t raised to -1. Maybe at most, let's put it. Okay. Now still, yeah, we say it is, we may complain. It's so complicated, each expression we write down so long things. But what this makes sense, it's easy to verify it is correct. The next, we try to rewrite it, to regroup it. We use a very simple relation, elementary relation. That is, we rewrite just as one term, but I make it very complicated. E raised to we say alpha n plus r multiplied by a sum over m. By the orthogonality relation, this is correct. Then, just for this single factor, we replace this. Then we put it, we make substitution, insert this relation into this here. We change the order of summation and the integration, and we regroup it. What we get. I need to keep formula 2. We said into formula 4, just rewrite. We find I is equal to, now let's keep these factors outside. Now we have and here it is, because here this one involves both n and r, so it's still a little complicated. Let me write down. This is an or an bar e alpha n. Here, let me write down it. I say it is kn alpha, and then another is the summation over m plus the arrow, something, the same arrow, plus this arrow. I'm not going to say something more. Then what is the k of n alpha? Let me write down it.
Yeah, there's an extra summation still.
Mm-hmm.
K has got a sum in it.
Yeah.
Because you've now taken two sums, you've made a third sum.
Yeah, then the inside the k, the kernel is we're taking the sum over r. K is equal to because we say here we have a factor e of alpha r, then together with this one, r exponential, then this is another one. And here we can say, because if the r square is large, this factor is very small. So it is, we first make a restriction, r is less than something, absolute value less than capital R, because we need to make this approximation. But now we can get this Poisson summation gives, it is equal to what? Let me write down it. Using Poisson summation, somehow it is a little complicated. So, but here we assume alpha is between 0 and 1. And we may ask, the Poisson actually is not equal. Poisson, yeah, you say it should be sum. We may verify the sum, only one term remains. All other terms are very small. But we have this condition. So Actually, it is a sum, another variable from minus infinity to infinity, but only one sum makes sense. All others are very small. So this one, we just say we get some bound is, we have this relation. K, this kernel, it is less than, actually it is trivial. Because here we have n, we have data. It is trivial. But it is very small, very close to 0, unless this is small. So it is very small if alpha is not in this interval. Let me just write down maybe 100 t over n. But we assume alpha is between 0 and 1. We say this is equal to j. So now let's see here. This we have another first arrow, we don't worry. This one is fixed. And this one, we find that this kernel, unless alpha is in the interval j, it is very small. But now the only thing is that here this kernel depends on n. But from this expression, we find that it is almost taught because something like this. So we get the transition formula. We use the partial summation over n, something like this. So the result is alpha is less than or equal to, here we have a capital N over delta, but this delta is cancelled with that delta. So here we take absolute value. Here, because we use the partial summation, so we may take a maximum. So we say the n prime is between n. Now it is the integral, but the integral is taken on the very short interval, which is j. So here it is just, we said the maximum. What's the label? Should it be 5 forces? I can't remember. Yeah, it should be 5. Another arrow. But the second arrow, we did it, we use approximation. This is our so-called transition formula, just like this. I didn't give it at the very beginning, but now we just got. Let's see what we have used. Actually, I didn't use anything more. At most, we use the Poisson summation, right? But maybe this is it. I think this should be a trick. Just rewrite. Because this is in the number theory, we say the so-called the technique of separating the variables, something like this. So now let's see.
Suppose a and 1, then you're going to apply this now, right?
No, I just mentioned some potential applications. So now let's see. Of course, if a n is equal to 1, that should be trivial. But it's a number n something. Let me say. So we say compare with the formula 2. Where is the formula 2?
N times the sum of the square.
Yeah, here. This is formula 2. Here, this is summation. So here we say it is, I erased it. It is the integral is equal to the integral from 0 here.
The formula, so if you extend j to the full interval, you get.
Yeah, we improve. So this should be sharper than formula 2, because with such just arrows here, we just sharpened the length of the interval. Originally, it should be from 0 to 1, but now it is the length. So what we can say is, if we ignore this arrow. This arrow, we don't worry so much. We may make it more precise. And the maximum over the n prime. Then what if we can prove maybe we allow the a, maybe something like the t raised to, that doesn't matter. This implies the sharp for certain one. Now the next, we just say something about that. Mainly, I concentrate on the way if the coefficients like the divisor functions, that corresponding to maybe the fourth power or the power of zeta multiplied by an arbitrary, something like this. For these things, what we can do is, eventually they reduce to the closed-man sums. It's somehow similar to the previous work due to Ivanich and in 1980s, the mean values. And maybe we may get something new, maybe. But let me say something.
Are you planning to, say AN is tau 2 n, then would you plan to estimate the integral by taking supremum of it, maybe not tau 2, something which hasn't got a main tau. Then would you estimate that by the maximum times the length of the interval?
Yeah. If the AN is the tau 2 of n, purely it is simple. But correspondingly, if the Dirichlet polynomial is multiplied by something else, some other, that's more complicated. That's we use but eventually the things is reduced to closed-man sums. So the last one I would like to say, although this result may not be let's consider that A sub n is equal to numbered n, O modules. Okay. And we assume the alpha is in the, just we say the alpha is between some C2 or C1. The order is the T over n. N is equal to T raised to C, so it's C greater than 1. So this is smaller one. Then we can prove that we say this is known. We have an upper bound. First by V. Let me give it. Maybe we have some logarithms, and that doesn't matter. Maybe something that doesn't matter. But this one. Let me say, for such a linear exponential sum, there are various methods to prove it. The first, it was given non-trivially by Vinogradov. Then the Vaughan, they simplified or refined his argument. But these are just combinatorial arguments. Another approach is by the Linnich to reduce to the zero density estimates of the Dirichlet L functions. But they all give the same bound. Now, what I can say, if it is less than, we save a very small power with some, maybe it is a small constant. But is it correct? Actually, if we assume the Riemann hypothesis, it is correct. Then this implies the weak Riemann hypothesis. Oh, actually, it is equivalent to the weak Riemann. There is a constant, maybe very small, just left to the no zeros.
Quasi.
Yeah. Actually, this is equivalent. But here, about this one, let me say, I found something for certain very intrinsic reasons. All known methods are unable to improve this bound to get this. But maybe something else. Sorry, maybe it's so complicated. Why? We say this is analytic number theory. The expressions are always very long something. Any question?
If you wanted to compute the fourth power moment of the zeta function,
Mm-hmm.
would this method simplify somehow the computation?
The fourth moment, actually, fourth moment itself has been proved, right? And maybe the question is the error to improve the error.
To just get the asymptotic with this transition.
Mm.
What do you mean by the asymptotic? The first term is with the power saving or without the power saving? That's very easy by a difference.
Yeah, but I want to kind of.
He will get, I'm sure this will lead to the off-diagonal first amount sum directly.
This can't avoid this. Because there's a method which avoids it.
Actually, we say the fourth moment, we try to just to find the up bound.
You have to square root the result.
Multiply by another Dirichlet polynomial. Maybe it's a square.
But now he's multiplying by, what is that? That's
Something else. We only try to find the up bound for this one. That should be valid.
then what? I don't understand. What are you saying?
Mm-hmm.
What's the claim?
We claim that, let me write down something like this. Say the M of S is, we say, n less than, we say the capital X. We may assume the an is even less than equal to 1. That doesn't matter. And depending on the x, x is a power of t. We claim this is less than. And what we have known, but we may need some extra conditions on the coefficients. If C is less than 1/10, that's by UNH. And that what's that name? Yeah, what's that name? The French Dirichlet. I don't know how to pronounce it. Sorry. But can we say make it say C is equal to 1/3, maybe even 1? For this one, is this also correct? If C equal to 1/2, this is correct. Then at least for the order of the zeta, we can get some very good result on that.
This is not for 1/4.
Hmm?
This is not for 1/4 by the work of 1.
Right?
It's not for C 1/4.
C is 1/4. I don't think it's C equal to 1/4. I don't think it is. I don't think it's. No, it's not proved. It's very hard. We may check it. We may check it. But if we, to find an upper bound, if we transfer it, we put a weight or something, that by the certain technique to transfer it to this one, that should be something should be very interesting. Some Klosterman sums or some expressions involves Klosterman sums. They should have certain cancellation, but still it's hard to say. Thank you.